Thank you for the invitation for this nice conference. I am Philippe Jacquet. My co-author, Véronique Joly, is kind like Jean-Marie Souriau because she graduated from École Normale Supérieure and worked in ONERA on quantum mechanics and chemistry in reentry shock. Unfortunately, she could not come. So that's only me. So this is the plan. I hope I will be able to make it. First, let's review very quickly the anatomy, what is believed to be the anatomy of a black hole. So a black hole is made of central singularity, where all the mass is supposed to be concentrated. In fact, we are not sure anymore, but and it is a volume 0, which is kind of strange, but it is life. And around it, there is this virtual hull, which is the event horizon. It is not an egg. It is not. It is just a border, a virtual border, under which the light cannot escape, beyond which the light can escape. The radius of this event horizon is proportional to the mass of the black hole with this formula. In fact, it is 2 times the mass if we consider Planck unit. From now, we'll use only Planck unit because I'm very lazy. As a Planck unit, these are the remainder of the Planck units. They are very unreasonable, except for the Planck mass. But all the other, the Planck length is very small, the Planck time is very small, the Planck temperature is very large, so it's not reasonable unit. But it's amplified. In classic life, I will say in normal life, the reasonable life, the black holes are eternal. Nothing can escape. So they can only swallow matter. So their mass increase, and everything which has been swallowed stay inside. We don't know in which shape, but it stay inside. But the quantum black holes have the property that it can evaporate via so-called Hawking thermal radiation. Therefore, if they can evaporate, it means they can lose mass. If they are isolated, they don't swallow any mass. If they can gradually lose mass, and finally, eventually, they will disappear. By eventually, we mean a very long time, but they will disappear. Yes, it's a very long time. And the time to the temperature of the black hole, since it has thermal radiation, has this formula. It is the inverse of the mass, and the time to evaporation has this formula, but still in Planck unit. In Planck unit, you see, we can reach this kind of lifetime. Here, very quickly, I collected some facts about this the black holes. What we know is the central galactic black holes. Every galaxy has a central galactic black hole. They call the garbage bin. So they are huge. They can contain 10 billion suns. The radius is large, can be the 1,000th of a light year. The temperature is completely unreasonable. Small, and the lifetime is of course very large. Also the massive star, when the massive star collapses due to the exhaustion of nuclear fuel, they can collapse in a black hole of 10 solar mass. In this case, the radius is 30 kilometers. Very small temperature. if our sun will be a black hole, it will be of radius 3 kilometers, our planet 3 centimeters. The moon. Or the moon is interesting because its temperature will be the temperature of the background of the fossil radiation. So, in theory, it could be detectable because the temperature is would be little above the background temperature. But the problem is that the size is simply ridiculous. It's the tip of a needle. Here, it is the Planck size of a black hole. We know nothing. Nothing is known because there it's a limit of quantum mechanics, and of course, there is a problem of the gravity, the quantum gravity. There is no theory, acceptable theory on this. We have only detected this kind of black hole. Here, the big problem with evaporation of black holes is the fact that if a black hole disappears, we lost the information was inside. Before the life was reasonable, what was inside the black hole could not escape, but it was there. Here, if the black hole evaporates, the information is lost. We can say, okay, the information is encoded somewhere in the thermal radiation, but the thermal radiation does not contain any information. The information loss, so we could say, okay, you lost information, you have your journal burned, you lost information, it's not a problem. In fact, when a journal burns, there is the ash, and the information is still in the ashes. So if the information is lost, it implies a quantum unitary violation. Oh, complete disaster. It means that it is possible to, from mixed state, to get back pure states. As if you have a memory made of spins, a flash memory, and if you can make all spins as pure state, you erase the information in the memory. It is as if was your system before you start to store information. The principle of unitarity. I am not expert in quantum information, in quantum theories. So what I understood, that should make me to understand, that in classic quantum you have a wave function. I start from the classic quantum. Of course, it's old-fashioned quantum mechanics. And the square of if it is correctly normalized, is interpreted as the probability density of the presence of a particle. This is a classic Schrödinger equation. Basically, it is the derivative with the self-adjoint operator on the wave function, and in normal life with a flat Newtonian state, this quantity is invariant because this is a self-adjoint operator. Therefore, the norm is preserved, and there is no loss of probabilities. That's good. So this is good. This means that the principle of unitarity probabilities always sums to 1. Yes, we know that the probability always sums to 1, but in this case, since the probability is related to some physical, there are discussions about this quantity, this is an assumption. In relativistic space-time, there's a density flow of probabilities. This density flow is conservative, and it is always unitary if the space-time is smooth without singularities. The problem that this paradox gave rise to a huge production of solutions. There is almost one per year. There are numerous attempts to solve this problem. Have been completely unable to understand the solution was proposed. But most of the solutions that have been proposed so far are the solutions which have preserved, we are preserving unitarity. Very few solutions were sacrificing unitarity. The most notable is the cosmology of Penrose. Why there are very few solutions proposing to sacrifice unitarity? Because unitarity is fundamental to quantum mechanics. If you want to violate unitarity, it is a curse. It's a completely. For example, there could be, you could have many physical descriptions. For example, spontaneous energy burst, the energy become amplified. So it means that if you have unitary violation, you may have the complete destruction of the universe. Of course, we don't need to be so pessimistic. We could limit the destruction to our galaxy. It's not. Therefore, very few people propose to sacrifice unitarity. Therefore, it means that something you can play with that without any risk, except that destroying the universe. So the Schrödinger equation so we are going to look at the semi-classic equation, try to solve the Schrödinger equation in a curved space-time. In the semi-classic situation, because we assume that the metric does not depend on the wave function, which is not true, because the wave function means that there is energy means there's a mass, means that the mass has an impact on the metric. Therefore, the semi-classic assumption is not true. But it's good enough for what we want to do. Here is the metric. On the metric, you can see that there is two singularities. One singularity is at the center of the black hole. But more interesting is when you are on the event horizon border. And this is this one we are going to look after. Here there is a zoo of metric. Beyond the event horizon is de Sitter metric. Within it is anti-de Sitter metric because you change sign here. Match-setting sign means that this become now, the time axis becomes space axis, and this axis, which is a radius, become time axis. We don't care because we are not going to enter the black hole. Here is a classic problem of the early age of quantum mechanics. We look at the harmonic solution of our Schrödinger equation. So omega is the harmonic solution. It's kind of parameter that describe energy. And if we translate into in spherical symmetry, so we forget the fact. Okay, so I go at full speed. Then you have this equation, and this equation, if you consider that we are close to the event horizon, then you got a solution. If the quantum length of the particle is smaller than the radius of the black hole, and this solution basically has a Mellin transform, and the Mellin transform has non-real solution. And this is the source of non-unitary solution. To have f as an L2 function, that's integrable, you need to have the imaginary part of omega r smaller than 1/4. It means that you don't need to have it equal to 0. So it means that it can be something non-unitary. And you can assume that this will be basically the main, when you take the square, will be the main contribution. And so it is as if you see the level of energy, but here you see the level of energy, but they stand in a strip with some imaginary part. So there's this quantity, T over 2R, is called it the unitary excess of the particle. 1 over 2R is the unitary excess rate. You see that it increases by 1 by each traversal time of the event horizon, so it is very big. It is very large, so it should have a physical impact. This is the question. And then even worse, if you consider that this is a cumulative linear excess of a black hole, in fact, you can consider this is NR, when NR is a number of particles. Here we consider only one particle, so how many particles are there in the black hole? We don't know. But we could assume that it is order of the square of the radius, because the entropy of a black hole is the order of the square of the radius. So if you consider the system with evaporation, that every time, every beta to r second, there is a particle which is emitted, and this particle is a loss of alpha over r, then you should have this equation for the unitary excess of the black hole of dimension r, but in fact this has no solution. Therefore, omega r should be infinite. It means that there is an infinite time between two emissions. It means that the black hole is again eternal. And doesn't emit anything. It's not a big problem, because here it is the only remind that it's the only black hole we have detected, and we don't know if there are actually thermal radiation. Second physical effect, so no flying stone. Here you take, we know that the unitary excess is infinite, but we want to compare what will happen if you choose to throw a mass to black hole of radius R1 or mass of radius R2. If there's a difference. If there's a difference, it means basically that all the stones, if it's infinite, will go to the closest black hole. So all the stones will fly, and the energy will, the universe will disappear. But in fact, we can use the same trick as for the vacuum energy. That is, these are infinite, but when we do subtraction, we got very small term. So the overall is infinite, but if we want to compare what we gain if we go there or if we go there, it is very, very small. And even if you decide, if a spin measurement decides a mass where to move, the spin measurement will be no longer 1/2 probability, but will be 1/2 plus this. It means that it is possible, in theory, to send information from this point in time to this point in time. But don't be so quickly happy, because if we take this figure with the smallest black hole that has been detected, which is 3 times the mass of the sun, it will mean that for each bit, it will be 10 to minus 125 bit per kilogram of mass. So this won't be useful for guessing the lottery numbers. Too bad. That's the bad news. And but however, we could consider what happens if the radius are small, but we don't know for the small radius. So the conclusion, very quick conclusion. Sorry, I've been maybe too long. Revelation of unitary is possible, or I will say acceptable, without too much disastrous consequence. As consequence, nothing is detectable with currently known black holes. Remember that the analysis is done in a simplified, semi-classic quantum model. I should say oversimplified. I will not add a dirty simplified. No, it's very simplified. The analysis will hold only for large black holes, because we consider for the semi-classic approximation that the event of evaporation should not affect the metric, not too much. Therefore, it's a very simplification. The theory about the tiny black holes, is not black holes very light, it's just a few tons, few thousand tons, is missing. Because here we are hitting the quantum gravity, and here we know nothing. When a tiny black hole evaporates, something strange, it emits a particle which has a larger mass than itself. So something has to be done there. So I will stop here. I hope I'm not too long.
So, are there any questions from the public? Okay, so if not, we will thank. Oh, sorry.
I'm sorry. I mean, maybe I didn't follow like all the details of the thing, but like, is this something like a theory of dissipative quantum systems then, or like? Because I also remember seeing something like that. For example, this Prigogine who had like this rigged Hilbert spaces where you could have decay. I mean, that was also a violation of unitarity, but he was not doing quantum mechanics, but you had that like decays in time where in his case was related with chaos, so you would lose predictability with time.
It is not decaying sorry.
I mean,
this is not decaying, it is increasing in fact, because you have solution with a positive unitary excess and those with the negative unitary excess. And this position of this solution, of course, if t tends into infinity, those with positive unitary excess will be preponderant against those with negative unitary excess. Okay. At the end, it is not decaying, it is really it is exploding.
Okay.
Any?
There was some debate around the LHC. So there was a doubt if we can have micro black holes. So is it something physically possible?
It's the honest answer is I don't know, because it is related to the very teeny black hole, and there is no theory. But if we extrapolate, because I read like you, but I have no clue on this. If we extrapolate the theory of evaporation, first they should evaporate very quickly, or if they don't evaporate, they will move at a speed which is close to light speed, so they will be out of the galaxy very quickly. But we don't know if the theory of teeny black hole is not yet established, which is too bad, by the way. But at least we are sure that the universe didn't, the Earth did not collapse after the experiment. That's the only thing that we know. Or maybe.
Okay, so let's thank again the speaker and